So today's seminar will be given by Aldair Alvarez, and on the topic of inventory routing and stochastic supply, or inventory routing with stochastic supply and demand. So Aldair is currently a postdoc with Jean-François Cordeau and myself at HEC Montréal, and he's the recipient of a Girard scholarship, a Girard postdoc scholarship. So that support is much appreciated. Aldair, he finished his PhD in March 2020. He did his PhD at the Federal University of São Carlos in Brazil on models and algorithms for inventory routing. And for his postdoc, he's actually continuing with this type of research on specific extensions of inventory routing and production routing problems. Actually, we know Aldair already from before because he was also a visiting student here for 1 year with Jean-François Cordeau and myself in 2018-2019. So we were very happy when he decided to accept our offer to come back as a postdoc. So I will give the floor now to Aldair. Yeah, the floor is yours.
Okay, thank you. Thank you for the introduction, and thank you everyone for being here. Good morning or good afternoon, depending on when you are. And this piece of research that I'm going to present you today was developed while I was still a PhD student, not too long ago, as mentioned already. And with the collaboration, of course, of my PhD supervisors back in Brazil and professors Cordeau and Jans. So this is the agenda of the presentation, so quite standard. I'm going to start with some motivation and the description of the problem that we are going to be addressing here, followed by the mathematical formulations and the heuristic method that we present for the problem, and concluding with the main findings of the computational experiments that we carried out for this research. So to start with, it's important to say, and this is not a secret, it is well known that research integrating multiple activities and decisions across the supply chain can lead to benefits for companies or those integrating that agreement. And in this figure, we show here some of the problems that appear in that context and some of the decisions that can be integrated in those problems, but we can have many more decisions like packing, cutting and stock, location, and so on. In particular, the inventory routing problem, which is the focus of our research here, basically integrates two main activities. On the one hand, the inventory management of a product, and then the distribution planning of that network. This problem appears in the VMI business approach, in which customers give the power of the inventory management to the supplier. So the supplier can manage the inventory level at its customers. And of course, there are some trade-offs involved in this exchange of power. And of course, it's expected that the supplier will manage this network in the most efficient way, leading to benefits for all the parties. And this is a problem that appears in many real-life applications, from very industrial applications like the distribution of gases in big volumes, but also in more daily life applications like the replenishment of vending machines and ATMs. So the problem that we are going to be addressing here. So this is the deterministic setting initially that I'm going to describe, has this structure, which is a one-to-many configuration. So one supplier and many customers. This supplier has a fleet of vehicles that can use to deliver the product to the customers. And the supplier works in a multi-period, finite, discrete planning horizon. We know also the initial state of the system. So we know the storage capacity, transportation capacities, and the initial inventories. And we are working under the consideration that we have a single product. Again, this is the basic variant. In each time period, the deterministic variant. In each time period, the supplier receives a certain amount of product that then it uses to satisfy the demands of the customers or to keep in inventory for deliveries in the next time periods. And also each customer has a demand in every single time period. And the decisions basically are first, when to visit each customer. So in which time periods we are going to visit each one of them. And then associated to those visits, we need to define a delivery size, so a delivery quantity for that delivery. And finally, vehicle routes, feasible vehicle routes for those deliveries in every time period. These decisions, they are interrelated. They need to be made in an integrated way. They are not sequential like that, but integrated. And the objective can be to optimize any metric that you can define for your system. Some additional important assumptions for this problem. So we work under the maximum level inventory policy, which basically means that we can deliver any amount to the customer as long as we satisfy inventory and transportation capacities. Also, the amount that the supplier receives in every time period can be used to make deliveries in the same time period they are received. So they arrive to the supplier facility and they can be dispatched right away. Similarly, the demands of the customers in, let's say, in a given time period, they can also be satisfied with deliveries in that same time period or through the inventory that comes from the previous deliveries. And also we have inventory holding costs that are charged both at the supplier and the customers at the end of every time period. So that was in the case of the deterministic setting, but we also know that, again, this is not a secret, depending on the context and type of information, ignoring uncertainties can have really bad consequences, can lead to poor performance. If we don't take uncertainties into account in the planning phase, then in practice, so in the execution phase, you will probably have problems. And this is the case for the inventory routing problem. For some of the information that you need to in the planning phase of the problem. So in particular, here we are working with the assumption that both demand and supply are uncertain, stochastic in this case. The demand uncertainty had been addressed before in this context, in the IRP context. But we found that, at least to the best of our knowledge, supply uncertainty had been neglected in the IRP literature. So we decided to investigate what will be the effect of considering uncertainty or neglecting uncertainty in the supply of the inventory routing problem context. Already highlighting, and I'm going to show this with the results of the computational experiments, that given the one-to-many structure, supply uncertainty can be particularly critical because disruption of the supply affect all the customers at the same time. So this is important to already be aware of it, and we are going to show that with the results. So we work with a two-stage decision framework, in which in the first stage, we basically plan our visits and routes. So we define all the routes of the planning horizon in the first stage. And then after observing the supply and demand realization, we define delivery inventory and the specific recourse actions that we need to make in that moment. Again, it's important to highlight that we know the supply and demand realizations before the vehicles depart from the supplier facility. So again, this is a configuration that we didn't just come up with. This is something that first has been used in practice, in the literature, sorry. Several papers have worked with this kind of configuration in the inventory routing problem context. And also this is in line with the practice in some industries in which you need to prepare beforehand certain resources, like your vehicle fleet, your drivers. You need to define that in advance. And then you define only when the time comes, you define your delivery sizes and so on. So this is something that aligns well with practice and the literature. So basically now with regards to the mathematical formulations, some notation first. So we have the node of the supplier, which is 0, plus a set of customers and a set of facilities, which is basically the supplier and the customers. We have a set of time periods, a fleet of vehicles, and a distribution network. And we have certain deterministic parameters like the initial inventory, the capacity, the storage capacity, and the vehicle, the capacity of the vehicles. We have inventory holding cost and travel costs. Then regarding the uncertain parameters, in this research, we are assuming that supply and demand are random variables, and that we know their probability distribution, which we assume is a discrete distribution. So we model that distribution using a set of scenarios, this capital S here. So for each scenario S in that set, we define this parameter RT, which is the amount made available at the supplier at each time period under the given scenario, and the demand of each customer in every time period. So this is the supply and this is the demand of the customers. And we have the probability of occurrence of each scenario, which have to be positive for each scenario and satisfy this property. So the first case that we considered was lost sales. So we basically plan our routes and visits in the first stage. And then for each unit of unmet demand in the second stage, we basically pay a penalty for that unmet demand. So we consider that as a lost sales. And a second case was an extra source of supply in the second stage, given a contracting option in the first stage. This is a production capacity reservation setting that I'm going to describe with more details next. But first, I'm going to focus on the lost sales. We propose mathematical formulations, make models for both cases, which we solve using branch and cut algorithms. So for the lost sales case, we have a penalty cost, which is paid for every single unit of demand that we don't serve for each customer and time period. And for the mathematical models, we have these variables. We have the classical routine and visit variables, which are first stage variables. And then in the second stage, we have some inventory level, delivery quantities, and unmet demand variables. Notice that they are indexed with the scenario S. So these are the variables of the model. So the objective function basically aims at minimizing the first stage cost, which is the routine cost, plus the expected second stage cost, which is given by the total inventory cost at all the facilities of the system, plus the lost sales cost for each scenario. So this is the weight of every scenario. We have inventory balance constraints for both the supplier and the customers. Remembering again that we have the supply here for the supplier in every time period under each scenario, and for the customers and the given demand for the scenario and the lost sales variable. This is the recourse that we use in the second stage. And then we have the classical constraints, imposing bounds on the delivery quantities and inventory levels, connectivity constraints, subtermination, and the domain of the decision variables. So that was the first case with lost sales as a recourse. But then we consider a second case in which, again, it's called production capacity reservation. And that goes like this. So the supplier has the possibility of contracting some extra amount in the first stage. So that's a first stage decision, contracting certain amount that will be available when required in the second stage. So that's the recourse. So the configuration of the problem now goes in this way. Having, in addition to visit and route planning in the first stage, we have the reservation of the capacity as a decision, it's a first stage decision. And then after we observe what happens with supply and demand, we define again the same delivery inventory and the lost sales, for example, which is a recourse. But we have an extra recourse here, which is this extra amount. It's an extra supply for the supplier, being redundant. That depends on this reservation. So if we do not reserve anything here, we won't have anything available. If we do reserve in the first stage, then we might have, we have that amount available, but we can use it or not, depending on what we want. Again, so that extra supply comes from an external provider and is ready if contracted. And this is, again, something that we didn't just come up with. This is something that exists in practice, in the literature in practice, and we're exploring for the first time in the context of the inventory routing problem. This kind of setting, which is a business-to-business agreement, has benefits for both parties, because on the one hand, for the supplier, the one contracting this extra amount, can benefit from having a cost that is lower than the lost sales cost, for example. While this extra external provider can benefit, can have better utilization of its resources by having this kind of agreement with certain companies. So to model this case, we have this first. We have that, and this is important, that the contracting capacity has to be a multiple of this base capacity delta here. So we are offered that delta capacity, and we can reserve that multiple times. So the capacity that we reserve is an integer multiple of this quantity. So we pay a fixed reservation cost for each delta units in the first stage, and in the second stage we pay a unit cost for each each unit that we actually use of that contracting capacity. So we have additional variables here, some notations. So V, which is the number of times that we reserve that extra supply, and the W, which is the amount that we actually use in the second stage. So adapting the model in this way. So in the first stage, we have now the fixed contracting cost here together with the routing cost. And the second stage cost is adjusted this way, in which we pay the unit cost for the amounts that we actually use. So in the inventory balance constraints of the supplier, we have the regular supply under each scenario. So this is a parameter depending on the scenario. And we have this decision variable now, which is the extra amount that we actually use as an extra supply at the supplier facility. This extra amount is bounded by the amount that we actually reserve in the first stage. So if we don't reserve anything, we won't be able to use that extra supply. And the rest of the constraints, they go the same. So given that problem, we also propose a heuristic solution method for that, which is based basically on the progressive hedging method. This progressive hedging method is a scenario decomposition approach in which I'm going to illustrate here with our case. So given the inventory routing problem with this set of scenarios, we basically relax the non-anticipativity constraints. So we decompose the inventory routing problem in independent problems for each scenario. So we have S problems here. And notice now that the first stage variables, they are scenario dependent, which do not satisfy the initial problem. So we decompose these problems, and within a loop, we basically solve these problems independently and make a series of adjustments, hoping to find a solution in which solutions actually for each scenario, in which the first stage solution of all the scenarios is the same, so that we reach that we meet the non-anticipativity constraints, leading to a feasible solution for the complete problem. To give you more details about it, so basically within a loop, we solve every scenario subproblem, and then we compute what is called a reference solution, which basically says or tries to identify the trend that most of the scenarios are following. So if we see that, for example, most of the scenarios are visiting a given customer in a given time period, then maybe we want the rest of the scenarios to follow that trend. So we apply a series of adjustments in the cost parameters of each scenario in order to guide the search in the direction of the reference solution. So we identify the trend, we update the parameters of each independent problem, and then we solve again. And the idea, ideally, you want to converge to this case in which all the first stage solutions are the same for all the scenarios. So you meet the non-anticipativity constraints. But since that might be too hard to reach within a time limit, for example, then you can impose additional stopping criteria like time limit, number of iterations, and so on. So those are the three main steps of the progressive edging method, but we also apply an additional step at the end of every iteration, in which we use one of these solutions of the scenarios to try to find a feasible solution for the complete problem. So that's the general overview of the method. We use a heuristic method based on ILS to solve both the individual scenario subproblems, but also here in the solution generation, feasible solution generation procedure, to try to improve the solutions that we find in that step. Now, some computational experiments. This is the configuration of the experiments to highlight. We implement in C++. We solve on the Calcul Quebec Compute Canada servers using Cplex 12.8 as the solver. For the instances, we use the benchmark set of Archetti 2007, which is a classical benchmark set for the inventory routing problem. We made a series of adjustments to make the instances less loose, because they can have like big supply values and big capacities. So to make it more realistic for our case. And we assume that the supply and demand values for the scenario generation using a discrete uniform distribution, the supply and demand values, they come from these ranges. So for the supply, in which this R bar here is the nominal value from the instance, adjusted, and more or less plus and less minus this value, which is given by this uncertainty level. So this uncertainty level defines the range, the width of the range that we use. So a larger uncertainty level, it means that the values, they can vary more or less for both the supply and the demand. And each scenario has the same probability of occurrence. So this is the basic configuration for the experiments. We used 20, 40, 60, and 80% as uncertainty levels. We used the instances with up to 30 customers, 9 time periods, and 2 vehicles. We generated, for each instance, 100, 200, and 500 scenarios. For the solver, for the branch and cut method, we imposed a time limit of 2 hours. And all the analysis that I'm going to present now, and they were performed using the solutions of those instances solved to optimality within this time limit. This analysis, the initial analysis, we have two sets. The first one is based on is focused on managerial insights from the results, and the second part is from the results of the heuristic. So initially, we wanted to explore for the lost sales case to see what happens when we increase the uncertainty levels of the solution. And this is what we show in this figure. So this is the first 2 columns of each set. They show the increase of the objective value, the cost of the solution basically, and the penalty cost associated to the solutions, the increase with respect to the case with only 20% as uncertainty level. So as we see here, as we increase the uncertainty level, we see how this cost and the penalty cost grows. And the third column of each set of each group shows in this axis the percentage of the total demand that is unmet, so that is lost sales. We see as well that with the increasing uncertainty levels, that amount tends to increase. And this is something expected, but what happens with the solutions itself? And this is an interesting finding. So when we increase the uncertainty levels, the solutions are changing in this way. In the first stage, we see that we're planning more visits in the first stage. So the number of visits tends to increase as we increase here the uncertainty level, and the delivery quantity in the second stage tends to go down. So this is what we call protection mechanism. So to protect against the uncertainties, the solutions are tending to a point in which you are planning more visits, so you cover more customers independent of the delivery of the supply value and demand values. You want to, okay, I don't know what's going to happen with my supply and my demand, so I want to visit more customers, and if I have product and if enough product to deliver to my customers, then I go and visit. Otherwise, I just like plan those visits and that are not used. So that's the protection mechanism for increasing uncertainty levels. And then we wanted to measure if that was accurate or it was relevant to consider the uncertainties in this context. So we computed this, the VSS and the EVPI, which are two basic, two standard like metrics in the stochastic programming literature. The VSS, which is the value of the stochastic solution, basically indicates what will be the gain of, what's the gain of the stochastic program with respect to a problem in which you ignore the uncertainties. So you use an expected value problem to estimate how worse your solution will be if you ignore the uncertainties. So that gives you that measure, the VSS. While the EVPI tells you how good the solutions will be if you knew the perfect information every time. So if you had, there was a way for you to know the exact value of the supply and demand. So how better will be your solutions? So that's what more or less those two indicators tell you. So we see that for increasing uncertainty levels, the value of the stochastic solution tends to increase as expected. But even for a relatively low value of the uncertainty level, we always have at least 19% a relative value of the stochastic solution. That shows that justifies the use of this stochastic program for decision making in this context, because it's important the stochastic solution has a relatively high value. While on the other hand, the expected value of the perfect information is always below around 3% on average for these uncertainty levels that we tried here. So showing that even if you knew the perfect information here, you will not gain a lot. So this shows the robustness of the solutions. And I'm not talking of robustness in the nature of robust optimization, but in terms of good solutions here provided by the model. And this previous experiment was with both, when we consider both supply and demand stochastic at the same time. But what happens if we consider just one of them at the same time, not both? So only stochastic supply or only stochastic demand here. And this first figure here shows how much the solution, the objective value, the cost of the solution and the penalty cost goes down if we consider only one of them. So as expected, solutions are cheaper and we have less penalty. if we neglect one or the other. But it's important to see how, if we consider only stochastic supply, this decrease here is relatively low compared to the case with only stochastic demand. So this is already giving us a hint that stochastic supply has a more significant impact on the solutions, given that if you neglect this case, you are neglecting stochastic demand, then your solution doesn't get much cheaper, much better. And we verify that in this second figure here, which are the features of the solution. So how the number of routes, visits, and the average delivery change with respect to these cases. So we see that when we consider only stochastic supply, so we neglect stochastic demand, the solution, the number of visits, the number of routes goes down, but always in a smaller proportion when compared to the case with only stochastic supply. So this is saying that, okay, stochastic supply has at least that's our conclusion, that stochastic supply has this significant or more significant impact when compared to the case with the stochastic demand. And we believe that this is given, this is a result of the pooling effect of the demand uncertainty, because for some cases we might have demands at the customer, let's say for a given time period, that is going to be higher than expected, but for another customer it's going to be lower. So they tend to compensate each other over time. So that's why demand uncertainty is not as significant as supply uncertainty here. And this is also, again, a result, as I said initially, of the one-to-many structure, given that supply uncertainty has that's this inconvenience of disrupting the distribution to all the customers at the same time. And we can also verify this pooling effect with this additional experiment in which, for a given number of customers, so increasing number of customers in the solutions, we analyze here, these bars show the objective value in relation to the cost when both supply and demand are uncertain. So a value of 100% indicates that the solution it has the same cost of the case when both supply and demand are uncertain, and below that, then it's just a fraction of the cost of the cost. So for example, for demand uncertainty, which is this one, as we increase the number of customers, this cost is going down. So it's getting far from the cost in which both are uncertain. So this is, again, showing in an empirical way this pooling effect. So we have more customers, their demands tend to compensate more each other, so the solutions get cheaper. On the other hand, for supply uncertainty, so the dark bar, we see that we increase the number of customers, these costs tend to grow, getting closer to the case in which both supply and demand are uncertain. So this, again, verifies the pooling effect. But even if you neglect supply uncertainty, for the case with only stochastic demand, the value of the stochastic solution is still important. So it's important to consider demand uncertainty, even though it is not as meaningful, let's say, in this context here. So that was for the lost sales case. For the capacity reservation contract case, and lost sales as well, so the two at the same time, we again analyze for increasing uncertainty levels what's happening with the solutions. So we have more lost demands, as shown here in the third column. But to try to avoid this lost demand, what's happening is that you're contracting more as you increase the uncertainty levels. And the procurement cost in the second stage is also going up. But we see that the contracting cost is growing faster than the procurement cost, that the capacity that you actually use is growing slower than the capacity that you reserve in the first stage. So this is an important observation to notice. And again, for increasing uncertainty levels, so the protection mechanism that we observed before consisting of increasing number of visits, the coverage, we're increasing that. We also increase the number of contracts that you use in the first stage. So that's now also part of the protection mechanism of the solutions. But again, highlighting that this quantity is growing relatively quick. And this might be a result of the modular nature of the capacity reservation contract case, because we need to make it an integer multiple of that delta capacity. Again, analyzing the value of the stochastic solution and the expected value of the perfect information, we see that as we increase uncertainty levels, this value tends to increase, making it more important to consider uncertainties, in this case, with both capacity reservation and lost sales. And the case of the expected value of the perfect information is now more significant. Before it was always below 3%, now it's growing with the certainty level, reaching values here close to 20%. So indicating that in this case with capacity reservation, you need to really take into account the uncertainties, because not doing it, it can be really costly as given by the expected value, but also as the expected value of the perfect information. And we can see that, verify that here, in which this chart shows in this line here up, we show the number of contracts of the solutions, which grows with the number of, with the uncertainty level. But if we neglect the uncertainties, so we solve a problem using the expected value of the supply and demand parameters. So we see that amount doesn't change. It remains relatively stable over time. So the solutions are not adjusting to this increase in the uncertainties, which shows why the value of the stochastic solution grows, and shows, again, highlights the importance of considering the uncertainties in this context. We can also observe the pooling effect here in this case with the capacity reservation contract. So as we increase the number of customers, the solutions with only stochastic demand, they tend to get cheaper, and the opposite for the only stochastic supply. And there was a configuration in which we had the same fixed cost, a given fixed cost and procurement cost, but those results depend on the cost configuration. So what happens, for example, if we fix the uncertainty level, but then increase the fixed contracting cost in the first stage. So if we increase it 3, 5, or 7 times a base value, so we see that the number of contracts, of course, if it's more expensive, you tend to contract less and you will acquire less extra amount, and that will result in more lost sales in every case. But it's important to see then that as you increase this fixed cost, the value of the stochastic solution tends to go down. This indicates that the model is being less reactive to the stochastic solutions, to the uncertainties of the problem, then losing value in terms of the stochastic solution. However, even for a case in which we increase by 7 times the fixed value, the value is still, the value of the stochastic solution, the relative value, is still high. So it again highlights that it's important to consider uncertainties in this case, and more importantly in this case, because you need to make that decision in a very accurate way, because that will then result in a loss, and very big loss. And this is also shown here by the expected value of the perfect information, which goes up with the fixed cost. So it says, like, if you knew the perfect information, you will gain a lot. So that means that you need to use the information that you have to make that decision and have the best possible solution in that case. And finally, for this insights part, given this capacity reservation contract case, we can also impose a service level indicating the maximum or the minimum, the maximum quantity of lost sales that we allow for each scenario. So we do it for scenarios. So we impose an upper bound on the total amount that we do not satisfy, given this kappa value, which says the fraction of the total demand of the scenario that we can leave unmet. We did it per scenario, but we could have done it per customer, time period, or customer and scenario, so on. But this is the case that we applied here. So what we observe here is that as we increase the service level, this kappa value, as expected, of course, the average lost demands, lost sales of the solutions, they go down, and the number of contracts goes up because you need to contract more to satisfy that service level. But it's important to observe that we don't need to impose a really high tight service level to reach a relatively low lost sales cost here, lost sales proportion here. Of course, for certain scenarios, you will have up to 10% of lost sales, maybe. But on average, the service level is very good already here. So you don't need to go to the extreme of imposing a 97 or 100% service level to reach an average value of lost sales here that is relatively low. And then on the final part, I'm going to show you some results with the heuristic method. So the first thing to highlight is that the heuristic can find feasible solutions for all the instances for different values for the uncertainty levels, while Cplex, the solver cannot make it within the time limit of 2 hours. And another important thing is like these solutions are found in a fraction of the time used by the solver. While in some cases we can have on average, this column here shows the relative difference of the solutions of the heuristic with respect to the solutions found by the solver. So we see that on average, for some cases, we are doing even better than the method. But if not, we are relatively close to those solutions. So it shows that the heuristic can find solutions with high quality within the time limit, even if we are dealing here again with 100, 200, and 500 scenarios, which is relatively high. This is for the lost sales case, but for the capacity reservation contract case, it's a similar scenario. It's a similar case. But more importantly, besides this quality in terms of the cost, we also observe that the solutions of the heuristic also follow these optimal policies, recourses, and mechanisms that we showed before. And we're going to show that a bit here, in which this experiment, we generated 10,000 scenarios, and we solve then using just a sample of those 10,000 scenarios, a sample of 10, 50, 100, up to 1,000 of those 10,000 scenarios. We took this sample and solved the corresponding stochastic problem with both the model and the heuristic, and then evaluated that solution found with this sample in the solution, in the model, in the set of scenarios of 10,000 scenarios. So we see here that these are the optimal solutions found by the model, the solid line. So again, like as we increase the number of scenarios, it's like increasing the uncertainty level. So we're considering more uncertainties. So we see that the first stage cost tends to go up, and the solutions of the heuristic, they follow the same trend. Of course, for certain cases, we'll have solutions that are more expensive, but they follow that trend. And also in the second stage cost. So that shows that the heuristics, the solutions of the heuristic adapt also to that policy. That was for the lost sales case, but for the capacity reservation cost case, we observe a similar behavior. However, it's important to highlight here that for the second stage cost, for this case of 700 and 1,000 scenarios, the cost of the heuristic, the second stage cost of the heuristic assessed on the 10,000 scenarios is way higher than the optimal cost. So the expected second stage cost of those solutions of the heuristic are way higher. So that's a warning sign of how suboptimal solutions found in the first stage can have a significant impact in the second stage here. And this is for the capacity reservation contract case. So it's a warning sign, but I would like to highlight that our heuristic was calibrated and tuned to solve instances with up to 500 scenarios. So it wasn't developed for this case, but even though we decided to show this to highlight how important it is to make accurate information and decisions in this context of the stochastic IRP with capacity reservation contract option. So just to conclude, to say that we proposed initially this formulation that can accommodate several recourses. We showed here how we used lost sales and also the extra supply in the capacity reservation contract case. In our paper, we also used an additional recourse, which was backlogging. But for the sake of brevity, I decided to not include those experiments here. But that framework that we show here adapts to several different recourses. We also observed, as it was shown with the results, how supply and demand have different values for taking uncertainty into account. They are both important, but we saw how supply in this one-to-many structure has a more important effect. We also observe how the capacity reservation contract brings certain flexibility to the system. However, these decisions, the contracting decisions, they need to be made in a very careful way. Otherwise, the consequences might be not nice. And proposed a heuristic method that can be used as a support tool to make decisions in practice in this context. And thank you for your attention. Thank you for being here. And I'll be happy to take any question that you might have. Thank you.